the relationship between the two estimators, alpha hat and beta hat. Basically, we'll be discussing about the derivation of the covariance of alpha hat and beta hat. What we have done so far? We have derived the distribution of alpha hat. We have derived the distribution of beta hat. But we didn't discuss how alpha hat and beta hat, how these two estimators are related. And we'll prove that the covariance of alpha hat and beta hat is equal to minus x bar variance of beta hat. How to do it? So this is beta hat. Already we have derived this expression for beta hat. Similarly, this expression we have derived for alpha hat. Now, when we say covariance of alpha hat, beta hat, it is basically expectation of beta hat minus expectation of beta hat into alpha hat minus expectation of alpha hat. Now, if alpha hat and beta hat are unbiased estimators, then expectation of beta hat would be equal to beta and expectation of alpha hat would be equal to alpha. Actually, I should put one more bracket here. When I put it in word file, I'll do that. So expectation of beta hat minus beta into alpha hat minus alpha. This is basically the formula for getting what? Covariance of alpha hat and beta hat. Now, what is beta hat minus beta? This is nothing but this one. And what is alpha hat minus alpha? Again, this one. So, covariance of alpha hat and beta hat is basically expectation of this into this. So, what we need to do? We need to get the mathematical expression of these components. And for that, what I need to do? I need to multiply this with this and this. You just see the multiplication. And then the second part is basically this. And then as you take mathematical expectation would be basically taken in this part because already we have discussed Ki is basically derived from Xi and Xi is assumed to be non-stochastic. So it will not have any mathematical expectation. So basically what we are doing here, like say here, this is summation of ui by m multiplied by summation of ki ui. So I can take 1 by n out of mathematical expectation, then what do I have? Summation of ki ui into summation of ui. And then we need to multiply it. Remember, when I am multiplying it, just take an example. Suppose this part is K1 U1 plus K2 U2 and this part is U1 plus U2 and multiply the two. So one part is K1 U1 plus K2 U2 and the second part is U1 plus U2. I'm just taking two observations for an example. So what will I have if I multiply? One part would be K1 U1 square, then K2 U1 U2, then K1 U1 U2 and then K2 U2 square. Let me just write it in Word file. Basically what I'm saying, the first part I'm talking about is basically like this. Say K1 U1 plus K2 U2 into U1 plus U2. Again, I'll write it down in detail. So when I do this, what do I get? I basically get this as K1 U1 square. This one is square. Then plus K2, this should be 1. K2 U1 U2 plus K1 U1 U2 plus K2 U2 square. Am I right? So this is basically, I can write it as summation of Ki Ui square. Then it will basically capture this part. If I write summation of Ki Ui square, it will basically capture this part and this part. And this is what I have done. You see summation of Ki Ui square, and then I have taken expectation inside. So basically it is Ki Ui square, and then as I am taking expectation inside, it is basically coming as summation of Ki expectation of Ui square. Now question is the second part, that is this part. And you know, when I take mathematical expectation inside, I'll basically have here K2, then expectation of U1, U2, again K1, expectation of U1, U2. And you know by definition, by assumption, expectation of U1, U2 is equal to 0. So by assumption, expectation of U1, U2 is equal to 0. So these two components should be cancelled out. So eventually I am having summation of Ki Ui square, and as I am taking expectation, mathematical expectation inside, basically I will have summation of Ki expectation of Ui square, and that is what I have written here. In the same way, here what is happening? I am having this into this, means expectation of X bar will not have any expectation, so I will have expectation of summation of Ki Ui whole square. And you know this is nothing but variance of beta hat. Already we have written that as variance of beta hat. You see variance of beta hat as this. So this component would give me variance of beta hat. So what I'm writing then, you know this is nothing but sigma square. So now I am having sigma square into summation of Ki divided by N minus X bar into this is nothing but variance of beta hat. And you know summation of Ki is equal to 0, already we have proved. So this part would be cancelled out. So eventually I am having minus X bar into variance of beta hat. And this is the covariance of alpha hat and beta hat. If X bar is positive, then you see the covariance is negative because variance of beta hat is positive. Variance of beta hat is positive. Okay, and normally what happens? We define this x and y in the first quadrant. We define x and y in the first quadrant. So x bar would be positive and there would be an inverse association, or say you can say the covariance between alpha hat and beta hat, that would be negative, given that variance of beta hat is positive. Is it clear? Is it clear?
Yes, sir.
Again, I'll write down the steps in detail in the Word file, because there is some missing part here. When I'm multiplying this into this, it's not simply this. There is an additional component. I didn't write it because mathematical expectation of that would be equal to 0. But when I'm just putting it in the Word file, I'll write it in detail. Every step will be written down. Now, next derivation is very interesting. I think in the last lab class, we were talking about this. Can you tell me what component of the last lab class we are talking about here? What component of the last lab class?
So we discussed that the correlation of y and y hat is the same
What is
as the
that known?
correlation of
What is that known as? What is that known as? Correlation
yes,
between
sir,
y and y
just a
hat?
minute.
Multiplier.
Yes, sir, right.
Now, here I'm going to discuss about this, that the absolute value of this multiple R is nothing but the pairwise correlation between x and y. The pairwise correlation coefficient between x and y. This is what now I'm going to prove. But remember, this happens in a bivariate model only. Means when there is only one independent variable. Now, what is the correlation between y and y hat? What is the correlation coefficient between y and y hat? It is basically covariance divided by standard deviations. And this is what I have written. This is the covariance between y and y hat. See, summation of yi minus y bar into y hat I minus y hat bar, divided by their respective standard deviations. I didn't divide both numerator and denominator by n because it automatically cancels out. Now, y hat I is equal to alpha hat plus beta hat xi. That means y hat bar is equal to alpha hat plus beta hat x bar. How I am getting this? Basically, you just take summation and divide by n both the sides, you will get it. Then I am replacing y hat I and y hat bar with this. You see the formula. I have replaced y hat I with alpha hat plus beta hat xi and y hat bar with alpha hat plus beta hat x bar. And then through mathematical simplification, I am basically getting this. This as the relationship between correlation coefficient between say y and y hat and that between x and y. Now it all depends on the sign. Otherwise, there is no difference. So if beta hat is positive, then both would be the same. If it is negative, then obviously one would be the negative of other. Just we need to add a minus sign. But overall, what we can say that the modulus of the two correlation coefficients would be the same. Now, why this is happening? Someone already told in the last class. That is what I have written down, that y hat I is a linear transformation of x with change of origin and scale by alpha hat and beta hat respectively. And you know, when we change the origin and scale of a variable, the correlation coefficient doesn't change in its absolute value. And this is what we are getting. So eventually what we are getting, that for a bivariate model, the multiple R, that is the correlation coefficient between y and y hat, is nothing but the absolute value of the correlation coefficient between x and y. Is it okay? Is it clear?
Yes, sir.
Now, I'll go for this derivation, but before that, I would like to discuss about this. It is little longer derivation. Here, basically, what we need to do, we need to get an estimator of sigma square. Remember, when we were talking about the distribution of alpha hat and beta hat, somebody asked yesterday that what is the purpose of having this distribution when we don't know alpha or beta? Yes, we don't know alpha and beta, but we can get an estimator for each of them. Like beta hat is an estimator of beta, alpha hat is an estimator of alpha. Question is whether we can get a similar estimator for sigma square, because sigma square is also unknown. I told yesterday that this sigma square is also unknown. We don't know ui. If we don't know ui, how can we know sigma square? Because it is the variance of ui. So question is whether we can get an estimator of sigma square. So here what we are going to discuss is basically derivation of an unbiased estimator of sigma square. Now, what we are going to prove that summation of u hat I square by n minus 2, summation of u hat I square by n minus 2, this is actually.
Hello.
तो हाइट से भी देखा होगा ना,
Reaction, can you mute it?
ऐसा
Thank you.
Yes, sir. Sorry, sir.
No, it's okay. It's okay. So sigma hat square is equal to summation of u hat I square by n minus 2. This we can use as an unbiased estimator of sigma square. But before that, we need to prove that this is an unbiased estimator. Now, what is this summation of u hat I square? This is residual sum of square. This is residual sum of square, this summation of u hat I square. What we term as RSS, residual sum of squares. And this n minus 2 is the corresponding degrees of freedom. So we can say this is mean of the residual sum of squares. And this we can use as an estimator of sigma square. Why? Because this is an unbiased estimator, and this is what we are going to prove. How to prove? We know yi is equal to alpha plus beta xi plus ui. If this is the case, then y bar can be written as alpha plus beta x bar plus u bar. Right? Remember what I was telling just some time back. We are not considering u bar is, we are not considering that u bar is equal to 0. So what we are doing here, we are basically taking an average of yi. And that gives us y bar is equal to alpha plus beta x bar plus u bar. Now, when we take deviation from mean, that is small yi, that gives us this minus this, alpha would be cancelled out. So what essentially we are having? Beta capital Xi minus beta capital X bar. So if I just factor out beta, then I am having beta into capital Xi minus X bar, which is nothing but small xi. So I can write that component as small beta into small xi plus ui minus u bar. Okay. So small yi, now I am getting it as beta into small xi plus ui minus u bar. In the same way, capital Y hat I is equal to alpha hat plus beta hat into capital Xi, and Y hat bar is equal to alpha hat plus beta hat capital X bar. Again, if we take deviation, then Y hat I, small y hat I, we are getting that as beta hat into small xi. Now, summation of u hat I square, that is RSS, that is equal to what? Summation of yi minus y hat I, that you know, that yi is equal to y hat I plus u hat I. That means summation of u hat I square would be equal to summation of yi minus y hat I whole square. At the same time, we know that y bar is equal to y hat bar. So basically what we are doing, we are subtracting y bar and y hat bar from yi and y hat I. You can see these two cancels out eventually, because we have already seen y bar is equal to y hat bar. So this essentially gives us summation of u hat I square as summation of small yi minus small y hat I whole square. And then you need to just replace these, what we have derived in 1 and in 2. So just replacing that, we are getting an expression like this. This we had already derived as small yi. You can see small yi as this, and small y hat I, right, as beta hat small xi. So small yi minus small y hat I, we can write it like this, and then this square. And then we need to just write it as, suppose this is A, this is B. So this is A minus B whole square, summation. So summation of A square, summation of B square, summation of minus summation of 2AB. And then for every component, we have derived it separately. Right? Now, what we have done for the first component? The first component is basically summation of ui minus u bar whole square, this one. Summation of ui minus u bar whole square, this is the first component. Now, what can we write for this? Ui minus u bar whole square summation. Again, this can be rewritten as a square plus b square minus 2ab. Now, if I take mathematical expectation of this, then I'll take basically mathematical expectation of this. Then summation of u bar square is nothing but n u bar square, because this is a constant. It doesn't have any ith dimension. So summation of u bar square is nothing but n into u bar square, and then this one. So if I just take summation and then mathematical expectation, it would be like this. Okay, and eventually it will give you n minus 1 into sigma square. In the same way, we can get it for the other two components, and finally when I add a and b and subtract c, then eventually I get an expression like this. And then mathematical expectation of sigma hat square, that is the estimator. That means mathematical expectation of this, which gives me sigma square. Now I'll stop here. I understand it's a very long derivation. Okay. And what I would suggest,